Okay, well, hi everyone to the graduate student colloquium. I'm glad you're here. Right off the bat, if you are interested in giving one of these colloquium or colloquia, just shoot either Christian or Pavel or me or all three of us an email and we can get you scheduled. I'm not sure if we have any slots open anymore this semester. I think we might have one or two. But we'll certainly note your interest and write it down for future semesters. So with that out of the way, I would like to introduce Alex Polanski. He's an astronomy student here, and he's going to talk about exoplanets, specifically, I guess, the exoplanet Wolf 503b. So take it away, Alex.
All right, thank you so much, Mindy. So I work with Ian Crossfield here at KU's ExoLab, and today, as Mindy said, we're going to be exploring the planetary system that I've been studying for about last year or so. But before we dive into this one particular planet, I just want to give a very brief overview of the methods of exoplanetary science for those who may not be familiar. And I apologize to those in Astro Seminar who heard a version of this talk last year. It's changed a little bit, so hopefully it'll still be entertaining. So the exoplanet field didn't really exist until the early 1990s when the discovery of the first exoplanet, 51 PEG, marked the start of a flurry of exoplanet discoveries, with the bulk of these planets being discovered in just the past 5 to 6 years. And that brings our total of known exoplanets to be over 4,000 at this point. And because of this, we now suspect that every star in our galaxy, on average, should have at least one exoplanet. For reasons that I'll mention later, most of these planets have been discovered by the Kepler spacecraft, which really began to shape our view of the exoplanet landscape. One of the most amazing discoveries to come from the Kepler mission was that the population of exoplanets, at least the ones on very short orbital periods, splits into two populations. The first of these is the so-called super Earths. So these planets have radii that can range from around 1.3 to 1.5 times that of our own Earth, and are thought to be mostly rocky planets with very little, if any, atmosphere at all. The other population over here, this other peak, is the Sub-Neptune population with a radii ranging from about 1.8 to about 3.8 Earth radii. And these planets are thought to have a very massive rocky core, actually much like the super Earths. But they also may be enveloped by a significant atmosphere that can make up about up to 10% of the planet's total mass. And before the 90s, most of what we knew about planet formation came from models trying to explain our own solar system, with rocky planets on the inside and large gas-rich planets on the outside. But the discovery of these two classes of planets and their ubiquity throughout the galaxy really forces us to ask some very interesting questions. How do these planets form, and why aren't they present in our own solar system? What effect does the host star have on the formation and evolution of these planetary systems? And finally, is there diversity within a single class of planet, or are all super Earths and sub-Neptunes essentially the same? And so to even begin to answer these questions, we need to know two things mainly about a planet. The first is we need to know the size, and the second is we need to know the mass, which we can use to obtain the planet's density. So to get the size, we rely on the transit method. So sometimes by sheer chance of geometry, the Earth, a star, and the exoplanet that orbits it are aligned in such a way that the planet will pass in front of its star, causing a very slight dimming of that star's brightness. Since we're only measuring the brightness of the star, it's really easy to just point a telescope at the night sky for a few months and wait for a bunch of stars to dim very slightly, which is exactly what the Kepler spacecraft did for a couple of years. So the transit method is a great way to sort of wholesale discover planets, which is why most of the exoplanets that have been detected with this method. So by measuring this dimming as a function of time, we can construct what we call a light curve, which is this red curve right here. And that can offer us a lot of important information about the planetary system itself. The depth of the curve is related to the scaled planetary radius. So this our planet over our star. So if you know the radius of the star, you just by simple multiplication, you're able to get the radius of the planet. If you're able to observe more than one transit event, a couple in sequence, you can actually constrain the orbital period. And you can even derive the distance between the star and the planet as well. So obviously a transit can tell us a lot about our own planet, about the planetary system, but it only gives us the size of the planet. Not really, it's not really good for making mass measurements. In fact, you can't get a mass measurement out of it at all, unless you have some kind of transit timing variation, but that's beyond the scope of this talk. So in order to get a mass, we rely on the method that's actually discovered the first exoplanet about 3 decades ago, known as radial velocity. So as a planet orbits its star, the star pulls on the planet to keep it in orbit. But as we all know from Newton's laws, no force goes unpaired. So the planet actually pulls ever so slightly on the star, causing the star to wobble as the planet orbits it. This wobble induces a Doppler shift in the spectrum of the star. And if we measure the shift and convert it into a velocity, we can obtain this sinusoidal curve, the amplitude of which is directly related to the mass of the planet. So this K is called the radial velocity semi-amplitude. And in reality, it's dependent on the mass times the sine of what we know as the inclination angle, which is the angle that this orbital, if you take the area of the circle of the orbit and project a vector perpendicular to it, the angle that vector makes with the line of sight to the observer is known as the inclination angle. But if we know that a planet transits its star, that gives it a special form of geometry that tells us that I is pretty close to 90 degrees. So if we can just approximate I is 90, this sine I term can be safely set to 1, and just by measuring the semi-amplitude, we can get a pretty good estimate on the planetary mass. So unlike transit curves, radial velocity signals can actually vary a lot visually based on the planetary system that we're studying. The typical radial velocity curve looks pretty much like a normal sine curve, which indicates it's just a simple one planet system on a circular orbit. So in this plot, you can just see this planet is going up and down, just on a very simple circular orbit. But some radial velocity curves actually show linear trends that are either increasing or decreasing with time. This is usually a sign of some long-term activity related to the star, or even a massive planetary companion that we didn't know about a priori. So here we see another very typical sine curve, but in this case it has a downward trend. So this sine curve could actually be imprinted on a much larger, longer period sine curve, of which we're only seeing a small snippet of right now. But what if a planet's orbit isn't circular? In that case, instead of a perfect sinusoid, the curve gets somewhat distorted because the planet's speed is changing as it orbits. Here we see that's distortion. We see that distortion with a long-term trend. As the planet's speed changes throughout its orbit, we get this very, very wonky sine curve. Finally, the most complicated model that we can sort of imagine for these planetary systems is one that has many different planets with many different periods and eccentricities, which creates a very messy signal that can eventually be decomposed with some effort into the individual planetary signals. So here we see a system with a few different planets. There's an increasing trend, so there's a lot going on in this radial velocity curve. Luckily, the planet that I analyze is just a simple one planet system, and it doesn't get nearly as complicated as anything you're seeing here. Okay, so with all this knowledge in hand, we can finally actually get to know the planet that I've been studying, so Wolf 503b. It was discovered back in 2018 by the Kepler spacecraft, and it orbits a fairly bright K-type star in the constellation Virgo. And since this was discovered via the transit method, there was no mass measurement for this planet. The Kepler spacecraft takes data in sort of two modes, a long cadence and a short cadence mode. The long cadence mode takes an image every 30 minutes or so, whereas the short cadence actually takes an image every 60 seconds. So you can see that here's a sort of time stamp here. So due to bandwidth concerns, most stars only have long cadence data available, which is what was initially analyzed for Wolf 503b in the discovery paper. However, there also existed some short cadence data for Wolf 503b that, for whatever reason, was never actually analyzed by the original authors, which is sort of a problem because if you have data with a lower sampling rate, you can't get as tight of a constraint on the parameters that you would get from that curve, as opposed to short cadence data, which is sampled every minute or so. So I won't spend too much time on the actual data reduction, but the process to go from pixels to a light curve includes performing aperture photometry on the star, so essentially summing up all the light within some number of pixels. And if we plot that brightness versus time, we get this very raw light curve with just a bunch of nasty systematics, which get modeled out and to get this nice, neat, normalized light curve, where we can easily see the different transit events spaced out at around roughly 6 days, which corresponds to the planet's period. If we go ahead and fit a transit model to this data and then fold the data in on itself every 6 days or so, we get this phase folded light curve, which shows the full curve in all its glory. This depth corresponds to a planet radius roughly 2 times that of Earth. So that's confirming what was originally found in the discovery paper. And if we notice how deep this dip is relative to the normal flux levels, we can see that this transit event only dimmed the host star by less than 0.1%. So I just want to point that out because it's pretty incredible that we're actually able to measure this. So in addition to observing the planet with Kepler, we also had the chance to use the Spitzer Space Telescope to get another transit curve in the infrared, as opposed to Kepler, which operates in the optical. So Spitzer was never really meant to study exoplanets, but after its coolant ran out, it was sort of conscripted into exoplanet follow-up science and actually proved fairly effective at this before it was shut down last year. So the light curve that we get produced a radius value that agrees pretty well with the one from Kepler. But since we were only able to observe this transit event once, we get no constraint on the period whatsoever, and all the other parameters are actually fairly hard to constrain. So if we're not able to get much out of this transit curve, why do we even bother observing this with Spitzer? The reason why we did that is because our ability to predict transit events tends to degrade over time. So the uncertainty in the time of transit is related to the uncertainty in the planetary orbit that we measure. So as time goes on, this uncertainty grows, making it hard to observe transits far in the future. However, if you are able to observe a planet shortly after its discovery, while the uncertainties are still small, we're able to further constrain that transit time, reducing that uncertainty as time goes on. So by using Spitzer to get another transit, we managed to cut down on the transit timing uncertainty by about a factor of 5. So that'll allow us to follow up with higher cost telescopes like Hubble or the James Webb Space Telescope if we so choose. And that's really important because time on these instruments is very expensive, and missing your transit event because your uncertainties are too large is actually quite embarrassing. So in this plot, we can see this blue shaded area shows the projection of the sort of 1 sigma mid-transit time uncertainty if we only used constraints from just Kepler data. But once you include a Spitzer transit in your data, that uncertainty drops by nearly a factor of 5, which is pretty good. So we know Wolf 503b's radius and the period fairly well. What about the mass? To get the mass, we observed the parent star at 4 different observatories over the course of around 1.5 years. So only knowing the radius of Wolf 503b, what kind of radial velocity signal can we expect? If the planet were mostly rock, the amplitude of the signal would be around 4 to 6 meters per second, that K value that we saw earlier. However, if there's a sort of a sizable atmosphere that's made up of volatile elements, that signal produced would be a little smaller, around 2 to 3 meters per second. But before we can kind of start fitting models to our radial velocity data, there's one other obstacle, the host star itself. So as it turns out, stars are not very quiet. They can induce a lot of noise in our data. And unfortunately, a lot of this noise can be periodic and actually mimic planetary signals. These signals can be caused by brighter and darker spots of the star rotating into and out of view, or small Doppler signals induced by variation of the stellar surface, which we call granulation. So is Wolf 503b's host star problematic? Fortunately, Wolf 503, the host star itself, is a K dwarf, which is known to be particularly quiet and amenable for radial velocity studies for exactly this reason. But we obviously don't want to take this on faith. And there's some analysis for our pre-data analysis that we can do to sort of get a closer look at any periodic signals that we may have to model out. To do this, we can take our data and create what we call a Lomsgargle periodogram, which is very similar to a Fourier transform in that it decomposes the data into constituent periodic signals. So what we have here in this top panel is the periodogram for what are known as S-index measurements, which essentially just measure the stellar activity of the star. And those measurements are taken alongside every radial velocity measurement we make. And those radial velocity measurements are decomposed here in this middle panel. So what we want to look for essentially is, do these two periodograms share any very significant peaks? So it turns out that the S-index periodogram is fairly quiet, with mostly insignificant signals, and most of these are essentially induced by the fact that we're not sampling our data uniformly. Most importantly, we see that with this vertical dashed dotted line, the area near where we would expect Wolf 503b's orbital period is fairly clear, as opposed to in the RV periodogram, as is to be expected, we get a very strong signal, which is a very good sanity check, making sure that we're actually able to detect this radial velocity signal. However, there is a fairly large signal in this stellar activity periodogram at very, very low frequency. And we'll actually, this will come up later on when we actually analyze the RV data. But on the whole, we can confirm that Wolf 503b orbits a fairly quiet star, which really allows us to focus on the planet signal when doing the modeling. So when we fit the radial velocity, we test the validity of adding different parameters to our model, starting with probably the simplest case, a circular orbit, and increasing the complexity to include eccentricities or some kind of linear trend, and to compare the different models and to make sure that we aren't overfitting our data. We use the KaiKey, I hope I said that right, information criterion, which takes into account the number of model parameters. So right here's the log likelihood function, and K is just the number of parameters in your model. So a lower AIC score indicates a better fitting model that doesn't overfit at the same time. To sort of compare two models against each other, we take the delta AIC, so the difference in AIC scores between them. And typically, if you have a delta AIC score of less than about 2, those models essentially describe the data equally well. If it's between 2 and 10, the validity of the one with a higher AIC score is sort of questionable. If it's above 10, the one with a higher AIC score can just essentially be flat out rejected. So the results of each model fit are essentially shown here. They're color coded according to the strength of the model, and we see that the best model that describes the data is one that describes Wolf 503b as being on an eccentric orbit and the existence of a long-term upward trend, which we can see very slightly in this data right here. Both models without a trend, so the worst performing ones, actually produce mass estimates that are fairly different than what would be for the eccentric trended model. So it's pretty good that these are outright rejected, because not being able to distinguish between two models that give fairly different mass estimates would be a problem. And the amplitude of the signal is around 2.8 meters per second, which places it squarely in the sub-Neptune camp, as opposed to a super Earth. So now that we're armed with both the size and a sort of mass estimate of Wolf 503b, we can begin to sort of place Wolf 503b in context. We know that it's roughly a 2 Earth radii sub-Neptune with a mass of nearly 6 times that of the Earth. These two values give us a bulk density of 2.79-ish grams per centimeter cubed, And for reference, that is about half the bulk density of the Earth. And so with the density, we can actually begin to speculate what this planet might be made of. But with only a bulk density estimate, this is still a very high degeneracy problem. There are many ways you can build a planet with different materials and still get the same observed properties. But it's still useful to consider some particular compositions. So here we've plotted radius versus mass for many different planets that we know of right now. And these lines here, these different colored lines, show theoretical compositions which match the mass and radius. So right here we have an Earth-like line. So all the masses and radii along this line would match in some way an Earth-like composition. This solid one down here would be a planet that's completely made of iron. These blue ones show different mixtures of water and rock. So the solid line up here would be a planet that's made 100% of water. This dashed one would be sort of 50% rock, 50% water. And these yellow lines show, are assuming some kind of planetary composition where you have a very dense Earth-like core, but is surrounded by a atmosphere of hydrogen helium. So in this case, that would make up 0.01% by mass of the atmosphere. So we can see that Wolf 503b, this red star right here, it's pretty close to a few different of these lines. We can see that it's nowhere near Earth-like. It's also nothing like the Neptune of our own solar system. So even though it's called a Sub-Neptune, it's not much like it. But if we are able to interpolate between these grids, we can actually get a rough determination for a few scenarios of what Wolf 503b might be made out of. So if we just assume an Earth-like core, Wolf 503b is consistent with either an H2O mass fraction of 57% or a hydrogen helium mass fraction of about 0.5%. So this water mass fraction might initially seem high, but actually some bodies in the solar system are mostly water. A pretty good example of that is Jupiter's moon Ganymede. So what this tells us about the planetary formation scenario for Wolf 503b is that it may have formed in a part of the protoplanetary disk, which is very far away from its parent star, and it accumulated a lot of sort of water ice. So when the planet was forming, it accumulated all this water ice, and that would be different than if the planet formed closer to its parent star, where all the water is evaporated. So there is this thing called the water snow line that separates the area of the disk between water ice and sort of water vapor. And planets that form within that snow line tend to be drier. Planets that form beyond it tend to be wetter, with water mass fractions that approach around 50%. So even though Wolf 503b is on a rather short 6-day orbit, this water mass fraction can indicate that it may have formed farther out in its system and then migrated itself back in. Another possibility is this sort of 0.5% hydrogen helium mass fraction. So in contrast to the last scenario, this might seem like there's no real atmosphere at all. But sort of in context, Earth atmosphere only makes up around 1/1000% of its total mass. And even Venus, which has an atmosphere about 300 times thicker than Earth, it still doesn't approach 0.5% of its total mass. So this is actually considered a fairly substantial atmosphere as a possibility for Wolf 503b. And since I'm running a bit quick on time, I can show a few more slides. So another thing that we wanted to do, instead of just looking at the sort of bulk density of this planet, now that we have the mass, we can actually sort of kind of get some scenarios about what this atmosphere, of what its potential atmosphere might be made out of. So if we look at sort of this transmission depth, this is how deep you can penetrate the atmosphere in a given wavelength. It depends on a bunch of different parameters. One of the most important ones is the surface gravity. Another one is the sort of mean molecular weight of the atmosphere. And another one is how much cloud cover does this atmosphere have? Because if you have a lot of clouds, light can't penetrate through the atmosphere in order for you to split it up and be able to figure out what it's made out of. So now that we actually have a mass for Wolf 503b, we can break a few of these degeneracies, because a lot of these three parameters tend to have a very similar effect on any transmission spectra, which can be seen in this plot right here. So as we go down, we can see that there are some bumpy features which indicate what the atmosphere might be made out of. But as we go farther and farther down, the spectra tend to get flatter, and they tend to show less features. So all three of these can have that effect. So once we have the mass pinned down, that's one less degeneracy that we have to worry about. And we can just worry on the mean molecular weight and the presence of any clouds or haze or any other scattering material. So to test that, we test a high metallicity atmosphere, around 100 times that of the solar composition, with a few different scenarios: a clear atmosphere that doesn't have any clouding, cloud or haze, a sort of cloud deck at 0.01 bar, and some kind of Rayleigh scattering effect. And so we also simulate those exact same scenarios for a low metallicity atmosphere. And we do that assuming we get to use the James Webb Space Telescope using these two different instruments. And skip that. And so what we find is, if we look at the simulated transmission spectra for Wolf 503b, sorry about that, we find that we can actually detect an atmosphere, which is important, regardless of metallicity, but clouds actually pose a problem. If you include clouds in your model, it's very hard to distinguish any spectral features from just a flat line. But since clouds are mainly a problem in sort of longer wavelengths, if we want to detect something like Rayleigh scattering, which affects more in the optical, we can see that this orange model here includes no Rayleigh scattering at all. It's just a very clear atmosphere. But this blue model includes a very strong Rayleigh scattering effect. So these transmission features are very differentiable. So we actually will be able to detect hazes in the optical for this planet. So I need to quickly go back. So sort of to wrap up, Wolf 503 orbits a very quiet K-dwarf star. It has a mass of around 6 Earth masses. It's about twice the size of Earth, and we've been able to refine its period good enough so that if we want to follow it up with more expensive instruments, we have the option to. And interior models indicate that it could have a very substantial water mass fraction or some sort of tenuous HHE envelope. So that's about it for my presentation. If you have any questions, please let me know.
Thank you very much, Alex. Are there any questions for Alex? Yes, Cole, go ahead.
Very random question, but how are these stars named? Like, is Wolf some guy, or?
Yeah, exactly. Wolf is some guy who lived, I think it was like early 1900s, and he cataloged a bunch of stars. And Wolf 503 just happens to be the 503rd or third star that happened to catalog.
Cool.
It also has a bunch of different designations, but not very important right now. But it is a very cool name, I'll give it that. I think it's one of the cooler named stars out there.
Brendan,
Yes, Brendan.
you have...
Yeah. Hi, Alex. So I think this was towards the beginning. You're talking about how a planet can make the host star wobble, and that can show up as like a periodic shift. So what I'm wondering is there a way, at least with current instrumentation, to differentiate between a planet and a smaller like collection of a planet and a moon, for example. So like, for example, the Earth moon system, our moon is pretty large in comparison to the host planet. Is there a way to differentiate just a large planet versus like a planet with a large moon? Or
I think that is actually an incredible question, and I think it would definitely depend on the mass of the planetary body and the moon. One problem that I could foresee is that um, as the planet orbits the star, that moon essentially is orbiting in the same is essentially following that planet around the star. So it might be hard to disentangle those signals just because they would line up so closely in phase space. Also, radial velocity is very, very dependent on the sort of the mass of the orbiting body. So unless you have a really, really massive moon on a very, very long orbit, I don't know. We definitely don't have the sensitivity right now. I'm not sure if we'll have it in, say, the next decade or so. But I think that's a really good question. There has been a lot of, there are a lot of papers about detecting exomoons with the transit method, actually. If I can kind of go all the way back here. If we go back to this one. So if we sort of imagine this planet having a moon, if somehow by some sheer chance the moon also is on the other side of the planet when this transits, you can actually see a slightly different light curve. So light curves might actually be the better way to explore exomoons than radial velocity. I hope that answers your question.
yeah, that was great. Thank you.
I have a question. I cannot raise my hand. But it's on one of the first slides that you were showing. I think it was the second slide. You're showing this plot of this figure. I found it very interesting to see like this structure when you look at this distribution, and I was wondering if there's what's the reason that you have a dip for the planet size at 1.8 Earth radii?
Yeah, that's a really good question too, and that's the that's a source of a lot of debate in exoplanetary science. But we sort of have settled into an equilibrium with two different solutions. And just to kind of keep it brief, there's it's either caused by photoevaporation of the planet by its host star. So stars are not just bright in the optical; they're also bright in sort of X-ray and UV light. And if you have a planet that's close enough, those high energy photons can eventually strip off a planet's forming atmosphere. And if you have a very sort of low mass planet that are associated with very small radii, it probably doesn't have the gravitational potential to hold onto an atmosphere in such a way that you can withstand this photoevaporation. But once you get up to higher planet masses, you're starting to be able to hold on to a little more of the envelope. So this bifurcation could be indicating the split between planets that are able to hold on to a tenuous envelope and planets that cannot. There's also another idea that, which is sort of related, except that the energy source is not coming from the star stripping off the atmosphere. It's coming from the planet itself. So planets can actually have some residual heat after formation, and that heat can strip off an atmosphere in sort of the same way as photoevaporation can. So those are sort of the two competing theories right now for this so-called Fulton gap.
Thank you very much. Yeah, it's very striking. When I first saw it, I was like, that's a very interesting.
Yeah, it's one of the coolest things to come out of that mission.
It's very cool. And I have one more. If there's no other question, I have one more question on this plot.
Yeah, please.
I see that there's like a faded line from this prediction for like these very low planet sizes. I was just wondering, will you ever get sensitivity in this region, like for very small sizes, or in the future, let's say near future, or?
Yeah.
Or is it a domain that you cannot really explore for the time being?
Yeah, it definitely gets harder towards smaller planetary sizes, and right now the only other mission that is doing sort of mass transit surveys is called TESS. So that's sort of the successor to Kepler, and getting below sort of 1 Earth radii is really sort of pushing it for our sensitivity right now. But sure, we'll be able to get there eventually.
Thank you.
Are there any more questions for Alex? I guess, yeah, if there aren't, thank you again, Alex, for giving our graduate colloquium. Yeah, it was really great, really interesting. Thank you so much. And again, if anyone is interested in giving one of these graduate colloquium, please give Christian, Pavel, or myself, just shoot us an email. All right, thanks for coming, you guys.
Thanks, guys.